In this lesson today, we're looking at extending on finding the areas between functions and axes. Essentially, we're just going to work through some more complex scenarios and look at strategies when we get integrals that can be simplified. So we'll start off with this first example, and we can see straight away, if we remember our patterns, that the graph of y equals 1 on square root of 4 take x squared relates to our inverse sine function. So what we're essentially looking for, and we can see here that it doesn't cross the x-axis. So when we're defining the area, it would just be the integral between -1 and 1 of our function 1 on square root of 4 take x squared with respect to x. Now the important thing to note here is that, so we should be able to see that this is an integral of 1 over square root of a squared take x squared with respect to x, which will be arc sine of x on a. So what we're looking at is a must be 2, and so we have arc sine of x on 2 between 1 and -1, which means we end up with arc sine of 1/2 and subtract arc sine of -1/2. Now arc sine 1/2 is simply going to be pi on 6. Arc sine of -1/2 will be negative pi on 6. And so we end up with 2 pi on 6, or pi on 3 units squared. To show you this in a graphical sense, we'll use our graphics calculator to confirm. You can see here we've got that graph of 1 over the square root of 4 take x squared. So if we want to then go g-solve integral, we can easily show that between -1 and 1 we have a positive signed area. That is 1.047, which is pi over 3. Okay, so that one's pretty easy if we recognize the pattern. That pattern is going to be really important. Of course, it's on our formula sheet, so we need to be looking out for that. When we look at the second one, we've got a similar scenario. With a little bit of manipulation, we should be able to relate this to a over a squared plus x squared with respect to x. Now, again, we want to graph it to make sure that it doesn't cross the axis. I know that it won't, but we still want to do that, so we'll quickly put this in. You can see here between -2 and 2, we've got this graph which is positively signed. So here's our limits. X equals -2, x equals 2, and here's the area that we're looking to calculate. So our area will be the integral of 6 over 4 plus x squared dx. Now hopefully here you can see that since this is a squared, a must be equal to 2, which means we need this up here to be 2 as well. So if we take a factor of 3 out in front, we end up with the area being 3 integral of 2 over 2 squared plus x squared with respect to x. And it's still between 2 and -2. So that means we end up with 3 lots of arctan of x on 2 between 2 and -2. So we've got 3 lots of arctan of 2 on 2 and subtract arctan of -2 on 2. So we end up with 3 lots of arctan of 1 and subtract arctan of -1. And so this will work out to be 3 lots of pi on 4, subtract -pi on 4, which is 3 lots of pi on 2, and we get our final answer, 3 pi on 2 units squared. Now, you could have recognized that there's symmetry up here, so we could have said that it's 2 lots of 3, the integral of 2 over 2 squared plus x squared, between 2 and 0, if that makes it simpler to calculate. So 2 lots of this area. We get the same outcome regardless. you can see we can adjust these slightly. Now, again, we can check this gsolve integral between -2 and 2. And we get 4.71238, and you can check that on your calculator. That will be the same as 3 pi on 2 units squared. Okay, moving on to example 3. Now it's asking us to find the area under an inverse trig function. So this gets a little bit more complex, and there's a couple of different approaches we can take. We should know what an inverse trig function looks like. An inverse sine in particular will take this shape, and it'll be bound by a domain. It can only be between -1 to 1 in that domain. So that means it needs to be -1/2 through to 1/2. So regardless, we'll sketch this. So we're looking for shift sine of 2x. We can draw that, and we can see that that's true. It's between -1/2 and 1/2, and the range is between -pi on 2 and pi on 2. And what we're trying to find, so show the region defined by the inequalities 0 is less than x is less than 1/2. Here's one of those regions. Oh, and it's got a second boundary between 0 and the function. So let's get rid of my shading. So between 0 and the function means that it's bound by those two inequalities, and we're looking at this region here. Now, I don't know if you recall, but in order to find the integral of an inverse sine function, you actually need to use a by parts process. So you can do that. We can look at the integral of arc sine 2x dx between 0 and 1/2, and we can go through our by parts process to get that integral. Or we can realize that we can find this area here between the function and the y-axis, and we can say it's, because this is pi on 2 here, we can say it's this rectangle. So rectangle, and subtract the integral. If we inverse this function, if we have y is equal to arc sine 2x, and we switch these, we get x is equal to arc sine 2y. So that means we have 2y is equal to sine x, and therefore y is equal to 1/2 sine x, which means we can say this is 1/2 sine y, in this case dy. So we're finding the area between the function and the y-axis, so we're looking at sine y dy. Now this is the approach that I'm going to take because it's going to be an easier approach. Now the boundaries will be between 0 and pi on 2. So our area is equal to this rectangle, which is 1/2 multiplied by pi on 2. Subtract 1/2 lots of the integral of sine is negative cos, and we're working between pi on 2 and 0. So we've got pi on 4, subtract 1/2 of negative cos pi on 2, subtract negative cos of 0, pi on 4, subtract 1/2 of, now cos pi on 2 is 0, so we've got -0, which is 0, and cos 0 is 1, so we've got -1, which is +1. So we end up with an area of pi on 4, subtract 1/2 units squared. Okay, in this next example, we're looking at trying to sketch the graph of y is equal to 1/4 take x squared. Now don't mistake this for 4 plus x squared. The integral of this cannot be an arctan function, so that means that we're going to have to break this one up using our process of partial fractions. Alright, so let's start by sketching this. We can see that it all exists above the curve, so we don't have to break it into parts. So we're looking at the function between -1 and 1. So it's quite shallow at these points. So here's our bounds, and this is the area that we're trying to calculate. Now, that means that we'll have to first consider this 1 on 4 take x squared as 1 on 2 squared take x squared, which means we're looking at it as 1 on 2 plus x, 2 take x. And when we break that up, we've got two linear factors on the denominator, so we've got a over 2 plus x plus b over 2 take x. Now, so that means we have 1 is equal to a lots of 2 take x and b lots of 2 plus x. When x is equal to 2, we get 1 is equal to 0a and 4b. So that gives us b is equal to 1/4. And when x is equal to -2, we've got 1 lot of 4a and 0b, which gives us that a is equal to 1 on 4 as well. So we can think of this 1 on 4 take x squared as being 1/4 of 2 plus x and 1/4 of 2 take x, or more simply 1/4 of 1 on 2 plus x and 1 on 2 take x. Now we can actually look at our area by examining the integral of 1 on 4 take x squared between 1 and -1, or by symmetry we could say that it's 2 times the area between 1 and 0. Okay, so let's do this now. We've got 2 lots of 1/4 the integral of 1 on 2 plus x and 1 on 2 take x with respect to x, which means we've got 1/2. The integral of 1 over 2 plus x is simply ln 2 plus x, and the integral of 1 on 2 take x, now we'll have to bring a negative out in front to make the numerator the derivative of the denominator. So this will be negative ln 2 take x, and this is between 1 and 0. So we have 1/2 ln 2 plus x over 2 take x between 1 and 0. That means we've got 1/2 ln, when it's 1 we have 3 over 1, and we're subtracting 1/2 ln. When it's 0 we've got 2 over 2. So 1/2 ln 3, and ln of 1 is always going to be 0, so this is our answer, 1/2 ln 3 units squared. So in this last example, we're looking at finding the area of the shaded region in this section, so we can see that's between pi on 2 and 3 pi on 2. And so really what we're looking at, because again this section doesn't cross the axis, is we're looking at the area being the integral between 3 pi on 2 and pi on 2 of cos cubed x with respect to x. Now of course this is a complex integral. This is, hopefully we can turn it into a substitution approach, so we can consider the integral of cos cubed x with respect to x as the integral of cos squared x cos x with respect to x, and cos squared we can treat as 1 take sine squared x cos x by using our Pythagorean identity. Now, here it is going to be a substitution if we let u equals sine x. So if we let u equal sine x, now we can say du dx will be cos x. So we've got that derivative relationship. Dx will be 1 on cos x du. And when we consider our limits now, so instead of being between pi on 2 and 3 pi on 2, our lower limit was originally we got x is equal to pi on 2, and so sine pi on 2 is equal to 1, so u is 1. When x is equal to 3 pi on 2, sine 3 pi on 2 is negative 1, so u is negative 1. So we can rewrite this and say our area is the integral between 1 and negative 1 of 1 take u squared cos x, and dx is now 1 on cos x du. So we cancel down here, and we have the integral between 1 and negative 1 of 1 take u squared with respect to u. So it simplifies quite significantly, and therefore we're looking at u take u cubed on 3 between 1 and negative 1. So we have 1 take 1 cubed on 3, subtract negative 1 take negative 1 cubed on 3. So we've got 1 take 1/3, which is 2/3, and we're subtracting negative 1 plus 1/3, which is we have 2/3, and we're subtracting negative 2/3, which means we end up with 4/3 units squared. So 4/3 should be our answer. If we use our graphics calculator, check again as we have with every question, and we're looking at pi on 2, so pi on 2, and 3 pi on 2 as our bounds. We can see we've got negative 4/3 there. Now you can see that my answer is 4 on 3 u squared, where the answer on here is negative 4 on 3. Now the issue is, if you look at my bounds here, I had flipped them. So I had 3 pi on 2, which is negative 1. So x equals 3 pi on 2, which is u is negative 1. I had pi on 2, which is u is 1. So technically I should have had the negative 1 at top and the 1 at the bottom. So flipping them, I've changed the sign and I've actually made it a positive area, which is what we were looking to do. So flip the limits, which changes to a positive area. Alright, so that was quite by accident, but it worked out nicely. Alright, that's our final example. Obviously you can see this increase in complexity in the integrals makes it a little bit more challenging. A lot of new little strategies, but also a lot of recognizing the patterns. In particular, make sure you take a bit of time with example 3, where we considered the inverse function, looking at the area between the y-axis and the function, which made it much, much easier to do. We didn't have to go through a by parts process. So this idea of finding the area between the y-axis and the function and subtracting that from a rectangle can simplify particularly inverse trig functions. Okay, so thank you for listening to the lesson. Make sure you spend time going over these processes and get to a point where you're fluent. Thank you.